We ask AI to do some pretty incredible things, right? From driving our cars to helping diagnose diseases. But have you ever stopped to wonder what's really going on inside the mind of an AI? Well, that's one of the biggest puzzles in technology today, and in this explainer, we're going to take a peek inside.
Okay, so neural networks. They're the engines behind pretty much everything these days. But here's the problem. For all their amazing power, they are often total black boxes. We can feed data in, and we can see what answer pops out, but that whole complex reasoning process in the middle, it's usually a complete mystery. And that makes them really hard to fix, to make better, and maybe most importantly, to actually trust.
And that's not the only headache. They're also notoriously bloated. It takes a massive number of parameters to get a network trained up properly, but once it's done, a whole lot of them are just useless. They're computational dead weight, making the models slow, expensive, and clunky to run. So we've got two huge problems. They're mysterious, and they're inefficient.
But what if I told you the key to solving both of these problems wasn't found in computer science at all, but in this kind of strange and beautiful corner of mathematics with a very surprising name?
Let me introduce you to tropical geometry. And no, it has absolutely nothing to do with palm trees or sunny beaches. The name was actually a nod to a brilliant Brazilian mathematician, Imre Simon. But what's really cool is that it fittingly comes from the Greek word trope, which means turning. And that idea of a turning point is exactly what this math gives us for understanding AI.
So, what is this stuff? Well, as a couple of researchers put it, it's like a marriage between algebraic geometry and polyhedral geometry. Now that sounds complicated, but here's the simple version. It's a way to take the complex, curvy, messy world of algebra and translate it into simple, straight-edged shapes. Things we can actually visualize and understand.
To see how this helps us with AI, we first need to get our heads around the fundamental shift in thinking that tropical math brings to the table. It's actually pretty simple, but it changes, well, everything.
Okay, so here's the part that's going to bend your brain a little. In the math we all learned in school, we add and multiply to build things up, to accumulate stuff. But in the tropical world, you just change the rules. Addition becomes finding the minimum of two numbers, and multiplication just becomes regular old addition. All of a sudden, math isn't about accumulating anymore, it's about optimization. Every single calculation is about finding the best path or the lowest cost.
And this whole act of translation has a name: tropicalization. Think of it like a new language for math. We take all the complex probabilities inside a model, hit them with a logarithm, and then we swap our usual plus and time symbols for their new tropical versions, min and plus. What we're really doing here is converting a problem of probability into a problem of geometry. So what in the world does this weird new math have to do with neural networks? Well, as it turns out, there's a really deep and kind of beautiful connection.
Here's the crucial insight. A huge number of the neural networks we use today, especially the ones using something called a ReLU activation function, they aren't actually computing these smooth, elegant curves. What they're really doing is computing functions that are piecewise linear. That just means they're made up of a whole bunch of different flat, straight-line pieces all stitched together.
And this is where it all just clicks into place. A tropical polynomial isn't some crazy curve. It's just the maximum or the minimum of several simple straight lines. And that is a perfect mathematical description of what these neural networks are already doing. The output of the network is a tropical polynomial. It's like the math was tailor-made for it.
So if a network's function is basically a tropical polynomial, and we know tropical math translates algebra into geometry, well, you see where this is going. It means we can take the entire complex function of a neural network and represent it as a single, physical, geometric object.
And that object is called the Newton Polytope. Now, this isn't just an analogy. This is the literal mathematical blueprint of the network's entire decision-making process. You can think of it as a shape you'd get if you plotted all the important numbers from inside the network, its slopes, its biases, and then just stretched a skin around all the outermost points.
So how do we actually read this blueprint? It's fascinating. Each sharp corner or vertex of this shape, it corresponds to a very specific combination of neurons all firing together. So when you feed the network, say, an image of a cat, the exact set of neurons that light up to identify it map directly to one of those corners. We've suddenly got a geometric map of the network's brain.
Okay, so we have a map of the AI's brain. That is incredible for just understanding it.
But it also gives us this incredibly powerful new tool to make it better. We can finally see which parts of the network are actually doing the important work.
The process from here is just beautifully simple. First, you take your big, clunky, trained network and you generate its Newton Polytope, its map. Second, you look at that shape and you identify the most important vertices, the ones that define the essential geometry and the ones that get used the most. And finally, you just throw away everything else and build a brand new minimalist network using only those key neurons.
And the result, you can potentially get rid of up to 90% of the network's neurons. I mean, that is a massive, massive reduction. You're turning a heavy, slow model into something lean, mean, and fast.
And hey, this really works. Researchers tested this on a classic AI task, recognizing handwritten digits. The original full-size network was 98.6% accurate. Pretty good. But after they used this method to strip it down to just a quarter of its original size, the accuracy was still over 95%. And get this, even when they slashed it down to just 10% of its original neurons, it still got over 93% accuracy. That is a gigantic win for efficiency, with a teeny tiny downside.
But really, making networks smaller is just the beginning. This whole geometric approach is so much bigger than that. It gives us a fundamentally new lens, a new way to see and understand what artificial intelligence is even doing.
With this new perspective, we can finally map out the exact geometric shape of a network's decisions. We can perform way smarter, more targeted pruning. We can even analyze those weird adversarial attacks, the ones that trick AIs, by seeing how they geometrically mess with the decision space. This could be the key to finally building AI models that are not just powerful, but are also robust and secure.
So in the end, by borrowing a tool from pure mathematics, we're doing a lot more than just making AI efficient. We're making it transparent. We're cracking open that black box and turning it into a blueprint that we can actually read, analyze, and improve. And that leaves us with a really fascinating question, doesn't it? Is geometry the language we needed all along to finally build AI that we can truly understand and trust?